hard, weren't they? At times, it's hard to know what you're talking about. Absolutely, you had to read. I mean, it was a tough one, and some of the questions were, well, this one fits, but man, what is he talking about? Pressure pushing molecules or that sort of thing. So the answers are there. Like I said, I don't think I'm going to make it that difficult. If you have questions, just ask about it, obviously. I'll go over it once it's finished. Okay, I see what you're saying. It's randomized. It really is randomized. I've got a bunch of questions. I guess you didn't get any. Cool. Lucky you. So yeah, I think I only threw a couple questions in that quiz regarding chlorination. All right. If there's no questions on that, what we're going to be talking about today is we have 3 lectures. One is a final review of everything. Second is, I mentioned that we have to cover all the labs. So because we have rotating labs, not everybody has completed all the labs. So we're actually going to just go through step by step and look for the key points, what you're supposed to get out of each lab. And then the final thing we have to talk about, and I do this every semester, is electrical safety for water technologists. So I am going to first open up for questions, general questions, and then we're going to start with electrical safety, the final review, which will take quite a while. I mean, there's a lot of slides here. And then the labs, which I was working on last night. Okay, do you still want our lab formals? Yes, in a nutshell. I don't want them because it's that much extra work, of course. But if you don't hand them in, you don't get a mark, and you could fail. Of course, everybody still needs 50% to pass the laboratory portion of the course. Yeah, whatever. Okay, any other questions? Actually, I want somebody, some brave person to unmute their mic. No, actually, we won't do that. I was just going to say how are things going generally with the other courses and classes? Does online lectures suck as much for you guys as it does for us? You know, that sort of stuff. Anybody want to? Okay, I guess that's good enough. All right, men and women. Well, actually, yeah, that's true. Easy to fall asleep. All right. The one nice thing about this is I don't have to brush my hair anymore, and that green thing stuck in my teeth, I don't worry about as much. But ooh, lab exam for bio next week. Good luck for that. Do you have to go in for that? Oh, virtual reality. Nice. Okay. I'm impressed. All right. Anyways, guys, and now it's just a middle quiz. Cool. Okay, let's start with electrical safety for water quality technologies. You guys have seen this before. It is going to be on the exam. As I mentioned before, the final exam, we don't know what's happening with it. The deans, nobody knows. So you guys know this already. Traditionally, all exams are in a format where you sit down and write for 2 to 3 hours, and just basically it's bulimic learning. You regurgitate everything that you've stuffed down onto a piece of paper. Now, we don't know if, chances are that's not going to happen. We don't know how things are going to happen. So things are still up in the air. But if worse comes to worse, this 2 hour quiz possibly might be okay, if the final exam, for whatever reason, doesn't happen. That will be up to the deans. So it's out of my hands. Any questions on that? Good. No, it's not your last lecture. We will for sure have one next week. Whether it's going to be during quiz or not, I don't think I'm going to get through everything today. But basically, yeah, we're at the end. We're because we managed to double up first, and good for you guys. We haven't missed a lecture or a lab, which is fantastic. We've actually doubled up our lecture time, which is great. You know, at the expense of doing these labs. And yeah, so you guys have worked hard, and because of that, we're almost done. If it's not a final, what will be the weight of the quiz? Whatever the quizzes are weighted as. Seriously. So I think 10%, 5%. It will be just thrown into the mix. But number one, it's an excellent practice for the final, number one. And number two, if for whatever reason the final doesn't happen, then I can use this quiz to get a good aggregate mark for each individual student. I have no idea at all. None. Zero zip. So I don't even think the deans. No, I don't think anybody knows. You know, it's every day we get emails talking about this emergency plan or whatever. It's going to come probably from the Educational Council, because this is a college institution. We have to follow the guidelines. Yeah. All right. Anybody else want to ask me a question that I don't know about? Please, I welcome it. I'm used to it. Joking, of course. If there are no more questions, though, let's do the electrical safety. I was talking about the final exams. I will, instead of asking general questions like, what is the safe current passing through the body? 10 milliamps? Or, sorry, dangerous. You know, those general questions. Because this is going to be an open book quiz and possibly an open book final, I will be asking more difficult questions. Have you guys work out the current passing through a body under certain conditions or whatever? So, overview, obviously, basics of electricity and circuits, hazards on effects of electricity on the body, specific hazards based on your field, and then conclusion. And I know everybody's seen this, but please, this is vital, and it's why I mentioned every year. Safety is so important, and electrical safety is difficult in the water engineering technology. So you can't see electricity, of course. You don't know if a wire is energized or not. The only way we can tell is by seeing the effects of electricity. Is a light on? Is a motor running, or whatever? Otherwise, it's impossible. It basically travels instantaneously. So at about 60% the speed of light in a copper wire. And of course it has no mercy. So electricity is the flow of electrons, voltage is the pressure that pushes those electrons, and current is the current flow in the circuit. You guys should know this and should be able to spit out these definitions, good definition. Be able to use Ohm's law. It's all defined here. I'm not going to go over it. If you want me to later, then message me and I'll show you how to apply Ohm's law. If a body touches an electrically live circuit and there is a path for that electricity to pass through the body and out, it will. So electricity will always try to find the easiest path to the ground. And I mean the actual outside dirt. Grab a shovel and start digging ground. So the Earth, our planet, is an unlimited, has an unlimited supply of electrons and can take an unlimited supply of electrons. And the way our electrical systems are wired, so we've got a generating station that will send electricity to our homes and factories, but use the ground as a return. Because of that, anytime you are touching the ground or something attached to the ground, you become a good conductor for electricity. So if you do touch something electrically energized and you do have a path to ground, you can be electrocuted, or you can suffer something called an involuntary muscle spasm. Electrocution is generally immediate death. Your heart shuts down, your lungs shut down. And muscle spasm, there are two types. One that causes your muscles to clench and hang on to the wire until your heart and lungs stop. And the other causes your muscles to contract and fling you away from this, from the electrical hazard. And sometimes, causing further injury. So, yeah, you have to know these electrical hazards. Burns, electricity passing through a body will literally cook the body from the inside, 4,000 degrees Celsius. And it follows along the path, nerve pathways, as well as blood vessels and stuff like that. Whatever is the least resistance, the path of least resistance. Also, burns, electricity causes fires, usually caused by improper use of extension cords. There's also something called arc blast, arc flash, and that is when the electrical potential becomes so great that it will actually cause the surrounding air to become plasma. And yeah, it's usually caused by a short circuit. So it's just a molten ball of flame. Explosions. Sparks can ignite fumes, dust, that sort of stuff. Fire, generally caused by faulty equipment. So simple house fires, factory fires, that sort of thing. The main concern for you guys is, of course, electrocution, shock. By law, nobody is allowed to work on any circuits that are greater than 50 volts. And even then, by law, you still have to be trained. Just don't do it. If you're not trained, if you're not an electrician's helper, that sort of stuff, stay away from electrical circuits. Call somebody. Even so, in a previous life, I was an electrician, considered a master electrician, industrial. I would have to put on a bomb suit, by law to test certain circuits, even protective equipment to test receptacles and stuff. So that's how critical safety is viewed with electrical systems, and you're not trained. Stay away from it. So the cutoff here is 10 milliamps. I mentioned that before. However, all of these are fair game. So if I ask at what current is ventricular fibrillation possible, you'd say from 17 to about 50 milliamps. All right, you can read the rest here. I will post this, of course. Oh, actually, I'm sorry, you guys have it. This just shows some calculations done using Ohm's law. So Ohm's law, of course, is based on the voltage, the current, and the resistance. So depending on the amount of voltage and the resistance that voltage faces, a current is generated. Generally, we run 600 volts in factories, about 120 volts in homes. And the human body usually is about 1 megohm dry, maybe a little bit higher, but it can drop down as low as 100 ohms. So if you do some of the math, for instance, 30 volts, and you've got a wet finger, 10,000 ohms, that will give 3 milliamps here. Yeah, there's not much to say. Just go over some of the calculations. So avoiding hazards, beware of signs, of course. Beware of all SOPs. Do not touch electrical equipment. Pure and simple. If you have to troubleshoot it, make sure it's disconnected, locked, and tested. Later on, I'll teach you how to wire motors and stuff like that, which you're not allowed to do, but possibly under certain circumstances, you may be required to do that. And there are a lot of safety steps that must be followed before that's possible, including being under the direct supervision of an electrician. So inspect wiring. If wiring's frayed or something, don't ever use it, number one, and don't try to fix it. Get somebody else, a professional, to fix it. Know the location of disconnects, shut-offs. Use GFI breakers, ground fault interrupt. That will limit the current to a maximum of 10 milliamps flowing through ground. So it is a lifesaver. The power strips and stuff, make sure that they have a circuit breaker or a fuse attached to it. Try to stay away from water. Pretty hard when you're in water engineering technology, but water is a hazard when dealing with electrical equipment. No lockout procedure. On equipment failure, reset breakers and overloads once. So overloads being motor overloads. Sometimes motors get bogged down. Breakers and circuit breakers. All these things tripped for a reason. So before you reset them, investigate why they tripped, try to figure it out, and then try to reset it. If you can't find a reason, try to reset it. It may be just a one-off thing. If it trips again, there's a problem. Call somebody. Figure it out. Otherwise, if you keep resetting, it's just going to blow equipment. Try to limit the use of extension cords. They are probably the major cause of fires and electrocution. Use only grounded plugs. If you see a plug where somebody has cut off the bottom ground, don't use it. Again, avoid water, and only use CSA or ULC approved equipment. Now, this may show up on an exam. What is CSA? So you want to write this down. CSA is Canadian Standards Association. ULC is Underwriter Laboratory of Canada. So CSA is the Canadian standards, obviously. All electrical code, all plumbing code, all pipe fitting code falls under Canadian standards. The Americans use something called Underwriter Laboratory, and it's similar to the Canadian standards. ULC just means it's approved in Canada, so we accept their standards. No electrical equipment without these two are allowed to be used. Okay, so conclusion, potentially kill instantly. Only authorized people are allowed to work on it. Inspect your equipment, assume electrical wires are live, and follow safety guidelines and SOPs. Oh, SOP, standard operating procedure. And that's it. Check my sources, please. Any questions? That was a nice short one to start the morning. Let's take a quick 5-minute break right now. I right now would like to start on the labs, even though this is electric portion. And unfortunately, like I said, I was up till 2 o'clock in the morning working on this. I have not finished it. But let's do this in 5 minutes. Go grab a cup of coffee, water closet break, whatever. I'll be back at exactly 9:30. All right, people. It's 9:30. We should get back to it. Give everybody a second to sit down and relax. Whatever. Oh, don't stop the game on my. I mean, at least finish this. Wow. Amazing. Another one. All right. Yeah, so we're going to talk about the labs. Some of the key points behind the labs. And when you guys, actually, I'm going to, so here is basically a list of all the labs that we have done. Now, I would like somebody to please talk about the make meter lab for a second. Who is brave enough right now to explain what the make meter lab was about? What was the purpose of the make meter lab? Anybody? Bloody heck. Okay, yeah. That's it. One of the things that students quite often don't understand is there is a lot of thought that goes into the design of labs, and these labs ideally will teach quite a few different things. So I'm going to now explain what I wanted everybody to get out of each lab and some of the key concepts that you guys will be facing out in industry. So obviously, like Aaron mentioned, meg meter, how it works. Now, I don't think I can, no, I cannot run these videos. I'm unable to run these videos in the PowerPoint because the PowerPoint isn't running. And I do not want to run it. I'm not sure if you guys will be able to um, to see it. So bear with me for a second, and I have to play these videos. So you guys know this already. A magnetic flow meter measures the velocity of conductive liquids moving through a pipe or conduit. So no moving parts makes it ideal for not just wastewater, but water, period. I mean, nothing really is moving, will wear out, can go wrong. And electronic devices generally last almost forever. Okay, so there are two coils inside, at least two coils inside a meg meter, magnetic flow meter. And each coil, when having current passes through, will generate an electromagnetic field. Inside the tube where the magnetic field is located are some voltage pickups. Generally, there are two, and the ones that we use have four. The reason there are four is it gives a good average of voltage, and in case the pipe isn't completely full, for sure one of the voltage pickups will be immersed in the liquid. And as mentioned numerous times, anytime a conductor passes through an electromagnetic field, a current is induced inside that conductor. In this case, the conductor happens to be some kind of conductive fluid. So a voltage is induced inside there, which is picked up by these voltage pickups. Oh. So now you just, the transmitter just uses Q is equal to VA. It knows the velocity of the liquid. It knows the cross-sectional area. Can get flow, Q. All these are considerations when choosing a magnetic flow meter. It's not part of the lab, but you should know that. Oh, incidentally, this video will be available on Moodle with the PowerPoint. And of course, I have to show them their name for such an awesome video. Oh, you can't see. Well, I guess I should have double checked to see that you guys could see the screen. You guys are going to get to watch this again. My apologies. So you already heard this wonderful, absolutely wonderful music. Yes, okay, for the first time. So my apologies. I will monitor the chat window as I watch this. Okay, and again, like I mentioned, these are some key considerations for choosing a meg meter, and this video will be available for you guys to watch. Okay, everybody should know the basic concepts behind the behind the meg meter. We've gone over it enough. So the second part that the meg meter talked about was the 4 to 20 milliamp control circuits. So 4 to 20 milliamp is commonly used worldwide it is lossless. So voltage is can be lost in wires. Current cannot. Current is the number of electrons flowing in a wire. And as long as there is no leakage in the wire, so no short or whatever, then if you have X number of electrons entering the wire at the start, you'll have the same number coming out. So current is ideal for that reason. If you have 100 meters of wire, you're going to have voltage loss. There's a resistance in that wire. Current is unaffected by wire length and that sort of stuff. Okay, it also has a live zero. So instead of using zero as zero, they use 4 milliamps as zero. And that way, if a wire falls off or something, you know that there's, or power loss, you know there's something wrong. 20 milliamps equals the maximum span. And those two numbers were chosen because they work out very nicely with computers. When put through a 250 ohm resistor, you'll have 1 volt, and when put through a 250 ohm resistor, you'll have 5 volts. And that voltage computers like. They just work well with that. So that's why a 4020 milliamp system is used. These are some of the questions that came from the lab. So why is the current of 4 to 20 milliamp used instead of 0 to 20? Live 0, 1 to 5 volts. You should be able to explain this. Explain the reasoning behind it. And if you have more questions, now's the time to ask. Or if you don't completely understand it, unmute your mic or please ask a question in the chat. 3 main parts of a mag meter, magnetic flow meter. Somewhat flexible with this one, but obviously a main one that has to be mentioned would be the coils, the electromagnetic coils. The second would be voltage pickups, have to have that. And then the tube that it passes, or a conductive fluid is fine, that sort of thing. But what I would prefer to see is coils, voltage centers, and a tube, and be able to explain how they work, what they do. What type of liquids can a mag meter measure? They have to be conductive. Honey won't work, petroleum products won't work. They have to have some ions in there that will allow current to flow. If the velocity slows down, you won't get a reading. You will not get a voltage reading. Usually there are 2 grounding rings before and after the mag meter, and that is to isolate any stray voltage. So because pipes are quite often plastic, well, PVC, a voltage can build up inside the fluid, usually from friction. And so this just isolates any voltage and sends it to ground, so that only the voltage induced from the mag meter is measured. Straight lines of pipe. In our class, it's 5 upstream, 2 downstream, just for the mag meter. Every instrument has their own needs. Type of calibration needed for the flow meter, magnetic flow meter, generally factory calibration. That's it. There's really nothing to calibrate with these. We're using a multimeter to monitor the voltage across the 250 ohm resistor. In factories, those wires will go to a 250 ohm resistor, but inside a PLC, an industrial computer. So it's the SCADA system that monitors. And I mentioned 4 voltage pickups instead of 2, as mentioned in the video. So our mag meters have 4, just in case the pipe is not full or to average out voltages. Any questions on this? Good. I'm afraid to ask if everybody's awake. No, I won't do that. Okay, so Second part, another part of lab 1 was, of course, how to use a variable frequency. So variable frequency drives are used throughout industry because they allow fine-tune control of pump speeds, ramp up time, which means how long it takes to get to full speed, ramp down time, how long it takes to go from stop to completely shut down, etc. And so this type of system, you get to play with it a bit. And there are some who were able to go in and change ramp up time, ramp down time, etc. And later on, you will learn actually how to program these and how to use them in second year. Good. That's lab 1. Lab 2, conductivity tester. So the purpose of this lab, the first one was to show that there are some instruments. Oh, incidentally, for lab 1, there are other things like orifice plate, differential pressure, etc. Unfortunately, because that lab is so poorly designed, it didn't give accurate readings for differential pressure and what, but at least it introduced you to the concept of how to read it. Good. Conductivity tester. Purpose of this lab was to, show that actually nowadays a lot of instruments are easy to calibrate. So this one is an easy one to calibrate. It's menu driven, and you just follow the menu prompts. So generally easy to read. Other part of it was how to use proper calibration and laboratory techniques. So obviously have to use standards, have to have clean equipment, including the instruments that you're using. So rinse it off with RO water into a rinsing jug. Label every container. Make sure you use proper chain of custody. So yes, you do. You need your name, date, etc. on every single piece of document, just to show that that you followed the proper procedures and that this instrument is calibrated and fit for use. And of course, safety. This one also showed that when you do calibrate, you want to calibrate close to where you're going to be measuring. And if there is no cheat sheet on how to calibrate or guides or whatever, you may have to create a little guide yourself. Also explained how conductivity tester works. Basically, conductivity just tests whether water is pure or not. Pure water does not conduct electricity, not very well. But as soon as you add just the smallest amount of ions, salts in that water, then water becomes an excellent conductor of electricity. So this is a quick and dirty way to see if water is pure or not. Should be able to explain this diagram, how it works. So a voltage source is applied to these, and if this water is conductive, you will have a current flow. If it is not conductive, obviously you won't. And there are varying degrees of conductivity. Some of the questions that came from this lab: why use a standard close to what you're going to be measuring? For accuracy. Be able to explain what conductivity is. And why can't more than one probe be placed in a container? Well, number one, these probes send out a voltage, so they can theoretically interfere with each other. And the second thing is, why would you want to? I mean, if you've got one conductivity tester and it's calibrated, that should be good enough. Any questions on conductivity? Okay, I threw in conductivity probe just because the lab does mention it, so you should be able to know, yeah, how conductivity probes work. So that brings us to lab 3, the temperature. Now this one, the purpose behind this lab was to teach the basic theory behind automatic control, learn the most important parts of a control system, understand the basics of data logging, and troubleshoot an error in a system. So really, temperature was an aside on these purposes. So everybody should know this, has to know this. And if I give a lab like the temperature, you should be able to say what the set point is, what the controller is, actuator, the process, the sensor, etc. So looking at this, the set point is obviously the desired temperature you want in the pipe. So you've got a heated pipe. The sensor happens to be thermocouples. The controller is the controller where the set point is actually put in and compared with the results from the sensor. The actuator is a solenoid that opens, allowing cooling water to flow through, and the process is just the pipe itself. We're, cooling the pipe. All right. So I went through this, what the set point is, what the controller, actuator, etc. This will be posted. I'll let you guys go through it. Went into a little bit of explanation of what thermocouples are. So they are basically just two dissimilar metals joined together. And also what a thermal well is. So this is a nice little diagram showing that a thermal well is just a protective covering to, put thermocouples or RTDs, sensitive instruments, rather than expose it directly to the process. I've got another video. So please let me know if you cannot see this. Okay, love that video. I actually love these little videos. It sums up the lectures that we've had really nicely. All right, so we also with this lab, you guys were introduced with the concepts of data logging. So in our case, we had a 4-channel data logger. You can see the picture of it right here. Newer systems look something like this. In our case, we had a 4-channel data logger, so we were reading temperature, but we could have read flow, level, turbidity, whatever. Each channel can be hooked up to an instrument. They can send out continuous stream of data, similar to a SCADA system, or just save all the data in internal memory and download them. yeah, just bring a laptop and download. So yeah, the idea, the concept behind data loggers. So questions from this that you guys have to know. What is thermocouple? Basically, it's two dissimilar metals joined together that will produce millivoltage, possibly microvoltage, um, based on the amount of temperature that is at the where the metals are joined. Name two other temperature sensors. I think everybody can do that. What type of maintenance does thermocouple require? Basically, just scaling on the thermal well and making sure that the screws are tight. It's just a wire. So if it breaks, replace it. Scaling, just like kettles will have a buildup of scale because of the evaporation of water. That can result an iron plunger allowing water to flow through or some fluid to flow through. Any questions on that bad boy? Anybody else as bored as I am? Just listening to me drone on? Okay, fair and square. No feedback. That's probably a good thing. Okay. DO analyzer. Again, the purpose of this was to show that some instruments are easy to calibrate, and this one was. It also gave the basic principles behind the LDO instrument. That was part of the lab itself. You were supposed to read how the individual instruments work, as well as a supplemental to the lectures. Examine other DO instruments, so like the handheld. You were instructed not to calibrate this one though, just because it takes so long to calibrate it. That's something you'll have to learn in the field. You're shown two older sensors technologies and given an idea of how to safely use them, calibrate them, etc. But no real hands-on, just literally looking at the polarographic as well as the galvanic sensors. So some of the DO questions, can technologists know the exact DO of a solution? No, it's pretty hard. The reason is it's constantly changing. It's constantly in flux. It depends on the atmospheric pressure, wave action, anything that will add or subtract oxygen to the system. Old DO probes are calibrated to the atmosphere. So what are some key factors when using the atmosphere to calibrate? Obviously, atmospheric pressure matters, temperature matters, elevation matters. You have to have a good idea of what the oxygen concentration in the atmosphere is in order to calibrate. Modern instruments, LDO instruments, figure it out automatically, which is so much easier. However, old style, you would have to actually look up on tables. And there is a question in the quiz that I just handed out where you do actually have to look at the table to figure out the concentration of O2 for calibrating. Let's have a break now, 10-minute, and we'll finish this off, and depending on how long it takes, maybe finish the very last lecture of the year. So 10 minutes, please, people. Do you want me to put the whiteboard back up? This would be a good time to ask questions. Darn, can't type. No, we won't be done the lecture today. I don't think we'll be finished today, Aaron. You will see. Thanks, Mike. You obviously type faster than me. Alrighty, people. Unfortunately, I'm going to kill this beautiful board that we have here. So, any other questions before I continue the labs? Now, the reason I'm going through the labs, like I mentioned before, is, of course, not everybody has learned the labs or being able to complete all the labs. You have done the required 80% of the coursework for the labs, especially considering the theory behind it. The practical, you have been exposed to different calibration techniques, so you're just going to have to pick it up. These particular instruments in the field. No calibration course, no instrumentation course can show you every single instrument out there. It's just the way it is. Just techniques. Can't see my screen. That's not good. I will change that. Thanks for letting me know. Okay, I'm assuming everybody can see it now. So the DO questions, continue them. Obviously, DO probes are calibrated in there, so you have to know factors that will affect the concentration of O2 in the air. Some reasons for DO probe not being accurate. So we're talking LDO probes, luminescent dissolved oxygen probes in this case. Needs calibration, probably the biggest one. Lens sometimes can get clogged, so just needs to be wiped. And sometimes cap main need changing. How often do you need to calibrate an LDO sensor? Maybe a year, once a year. You have to follow the SOPs of each place. And then know what tau and time constant for instruments are. And that's just the response time of an instrument. Some instruments are quick, they respond right now. Some instruments take a long time. And it's just a technique on what on how to measure the time constant. Cool. If there are no questions for that one, chlorine lab. So the purpose behind this lab was, again, teach the theory behind automatic control, learn the important parts of the control system, understand the amount of chlorine needed to chlorinate water, and understand how to calibrate a valve. So unfortunately, this lab, the sensor was faulty. It was supposed to be changed. I doubt if it still is changed now. It's going to have to wait till next year or when we're allowed back in the college. But it had a faulty sensor. But that was okay because the point of the lab was understanding how an automatic system should react and important parts of the control system. So again, automatic control systems, in this case, had, of course, the set point and the controller. The actuator was the chloromatic valve, weird, valve. The sensor being that faulty membrane type sensor. So should be able to identify the parts of this control system. Introduced to what a tunner is. Tunner just being a great big tank filled with liquid chlorine. Not the safest system out there, especially since water treatment plants are usually built in cities, but pretty safe. So also talked about the amount of chlorine that is needed. Really, you only need 1 drop of chlorine bleach in 1 liter of water. The minimum requirement if you are disinfecting, according to the EPA, so American government, is 2 drops of 6% bleach in 1 liter of water. Let's stand for 30 minutes. So you don't need much chlorine whatsoever. Pressure calibration. This is where, so at this point, it's about 1 o'clock in the morning, and I had to get up at 6 to prepare for today's lecture, and I'm starting to peter out. So I'm going to continue this and finish it off when it's done. I'll post it on Moodle. But the pressure instrument calibration, the purpose behind this lab was introduce the concept of 4 to 20 milliamp signals, introduce the concept of basic wiring. This is your first introduction to print reading, building from prints. Introduce how to calibrate a pressure transmitter using a hand pump, and introduce zero span calibration. So it's pretty hard to take a drawing or a schematic and build something from it, but that's what technologists have to do. It's a skill that must be learned. The only way to do it, to learn it, is to do it. And so this was your first kick at it. Later on, we will be looking at multi-page drawings of a water treatment facility and identifying key components of that. So this is a typical electrical drawing that you had to wire properly, and everybody did. Basically, there are no errors. But it also introduced a few other key concepts, like special instrumentation wiring. Electromagnetic interference from devices like cell phones, computers, all that can swamp signals in instruments. He also learned how to use the hand pump, calibration pump, and zero and span. So these are actual just buttons that will set the zero and then the span of an instrument. So shielded cables for instruments to stop any bad electricity from overriding the instrumentation signals, mainly because they're in millivolts. Grounding of instruments. So the farthest side away from the instrument must be grounded to get rid of all this bad electricity. How to wire instruments, multimeter use, review that, and setting zero and span to whatever level you want. If you want your zero to be at 25 kPa, fine, you can set it that. And your span at something, as long as the instrument can do it, you can set your span to whatever you want. pH lab. This one really, the purpose of this lab is, number one, to show you how difficult it is to control pH because of the titration curve. Show that, sometimes you have to calibrate an instrument that is terribly written, a manual. Show you that, if that's the case, you may want to write your own cheat sheet, a step-by-step guide on how to calibrate or how to operate a piece of equipment. So that's basically that lab. There wasn't too much to it. This one is a lab to show that sometimes instruments are bad, that they're poorly made, and suck it up, buttercup, that's the way it is. And hopefully most people got that sort of level of frustration from that lab. Level 8, this one, purpose of it was just to show 3 different methods of level measurement. concepts behind the bubbler, concepts behind the ultrasonic, and also introduced troubleshooting and error in the system. Actually, the temperature lab did that as well. And sorry, this is for my own temperature. Oh, I forgot to mention that. Anyways, whatever. So this lab, there was an error built into the lab, basically. The bubbler was entered the tank at a lower level, so it would have a zero offset error. And when graphed, it would become very apparent that there was a zero offset or zero reading error. And everybody in the lab was supposed to figure out why without help. And most people did figure it out right away. So that was a built-in error. And sometimes that happens. People miss something or whatever. And as a technologist, it is your job to figure out what is wrong. Engineers are only as good as their experience. You know, they go to school for 4 years, but when they come out, it really, they've got all this book knowledge, but what really counts is experience, just like everything else. You could train somebody for years and years on how to be a great chef, but until they actually pick up a spoon and a spatula, you know, they don't have the experience. Okay, so that was basically the level lab. Went into there was quite a write-up on the idea behind ultrasonics. I'm not going to go into it. I will include a video on it. What is a level sensor? I recommend you guys watch it. Talk about the bubbler principles, static head pressure, how it works, that sort of stuff. And then the last one was turbidity control, which was a great one because Frank has been an instrumentation guy from, well, for sure since the mid 90s. I'm supposed to know how to do this stuff, and I could not figure out how to calibrate it and still cannot figure out how to calibrate it. But the purpose of it was to be able to use the online videos and resources that modern systems have and be able to maintain and calibrate that system. So nowadays, companies are putting out YouTube step-by-step guides. So that was the purpose of this. And I think I got that purpose across. It's just unfortunate that their guide does not work with setting this up. I still am trying to figure it out. It's on hold right now because of COVID-19, but this is one of these things that will get done. And as a technologist, you may end up facing something like that. This instrument is not working, figure it out. That's your job. All right. That's basically it. Check out my sources if you want or don't. I will post this on Moodle. Any questions? All right. We now have about 26 minutes left. I'm tempted to stop there just because this is incredibly boring for you people. We'll do the final, and I'm sorry, but that's just reality. Let's do this final review next week. It is, even though this is a lab, you guys, next week, even though it's a lab, it is optional, although I highly, highly, highly recommend everybody attend this because this is going to be, yeah, basically your final review. If there is time and if I have the quiz written, it will be available to write. Otherwise, it'll be Monday. And yeah, what my suggestion is, if you guys have not tried the quiz, the turbidity, or sorry, the chlorine DO quiz that is online, try it now. Just see. They are randomized questions, so there's a bank of like 50 questions, and you only have 10 to answer, mostly on DO, and they are tricky. So do your best. I'm going to be online. I'll just mute my mic. So if you guys have any questions, ask away.